Good morning, everyone. My name is Nilanjan, and today I'll be talking about Xanadu, a platform to mitigate cascading code starts in serverless function chains. So, what are serverless functions and serverless function chains? Serverless computing is a new development in the field of cloud computing. It allows applications to be divided into smaller parts called functions, which run in isolation from one another. However, such a paradigm might be restrictive for complex application behavior. To mitigate that, serverless workflows allows functions to be orchestrated in different relationship behaviors. For example, one is to one, or one is to many, or many to one function chains, so that complex applications can be developed while providing the agility to scale them at a function level granularity. However, serverless functions suffer from something called cold starts, which is the time a function needs to wait while the resources are being provisioned. This problem gets cascaded in the case of function workflows. For example, let's consider a function chain of length 5. When a request is received for the function chain, the first function will suffer from a cold start. And after it executes, the request will move into the second function, which will subsequently again suffer from another cold start, and so on and so forth until the entire function chain executes. Thus, the overall overhead suffered by the function chain is a summation of the individual cold starts that was suffered by the individual functions. We deployed a chain of varying lengths and saw that this overhead increases linearly. And for a chain of length 6, the CCS overhead can go up to 48% of the total end-to-end latency. And this is not even a very rare phenomenon. We deployed an application which was to emulate a lightly loaded application behavior, and we deployed it on AWS and Azure. And we saw that 62.5% of all Azure requests and 78.1% of all requests to AWS suffered from CCS. To mitigate that, we bring in the idea of Xanadu. The idea of Xanadu is divided into three parts. First is that of mitigating cascading cold start. We do that by speculatively pre-deploying resources in the function chain so that the workflow does not suffer from CCS. Second idea is to reduce the amount of resources required to mitigate the CCS. For that, what we do is we reduce the amount of time the resources are locked in by using something called just-in-time deployment. And third, to further reduce resource requirements, we only deploy resources on the most likely path that an application might take in a conditional chain. So let's discuss about speculative deployment. Let's again consider the initial function chain example that we saw sometime before. Now, instead of deploying resources one after the other, as and when required by in a reactive fashion, over here we deploy all the resources at the beginning or at the onset of the request. So, even though the first function suffers from a cold start, the later functions only experiences warm start, and the CCS experienced by the entire workflow is equivalent to the initial cold start latency. However, as I already discussed, that this requires a lot of resources to be reserved at the onset of the workflow itself. To mitigate that, we discuss something called just-in-time deployment. Over here, instead of deploying everything at the onset, we delay the deployment of the resources to in a just-in-time fashion, so such that even though we do not suffer from cascading cold start, we do not have to reserve a lot of resources. And coupled with this, we also maintain something called a most likelihood path, which tells us what is the probabilistically likely path that is going to be taken by the application. And we only deploy resources on that application path. We developed Xanadu using Node.js and we will compare it with Apache OpenWhisk and Knative. The figure on the right shows us the different parts of Xanadu. The the boxes labeled in green are associated with the workflow level deployment, while the branch detector is associated with detecting the most likelihood path, and the metrics engine looks into how much time each function requires so that they can be used to uh, deploy resources just in time. Now we are going to evaluate Xanadu and its different forms, that is Xanadu code, that is Xanadu without any optimization, Xanadu speculative, and Xanadu JIT, and see what has an effect Xanadu has on cascading cold start and what are the resource requirements that Xanadu has to mitigate this cascading cold start. We will use the following metrics. One is the cascading cold start latency, or the CD cost. The resource cost associated with it, the CR, which is the CR cost, and they are divided into CR CPU, which looks into CPU cost, and the CR memory, which looks into the memory cost, and a joint penalty factor called phi, which looks at the joint penalty of CD and CR together to find out which form of Xanadu provides us with the best trade-off. First, let us look into the speculation benefits of Xanadu. We compare our results against Knative and OpenWhisk. The plot shown over here has function chains of different length on the x-axis, while on the y-axis we have the overhead latency, which is measured in seconds. We see that for both Knative and OpenWhisk, the overhead latency increases linearly, whereas in the case of Xanadu, the overhead latency is only for 1.11x, or 11% only. And on an average, this overhead lies around 15 to 20%. So Xanadu mitigates the cascading cold start problem. Now we look into the resource requirements for Xanadu. We see on the left is the CPU usage plot. The x-axis is a chain length, and the y-axis shows the CPU usage in milliseconds. The x-axis, as we move from along the x-axis, we increase the chain length, and we see that Xanadu speculative is more costly as compared to Xanadu cold. Whereas if we turn on Xanadu JIT, the cost decreases and it's only 0.9% more expensive than Xanadu cold, that is Xanadu without any optimization. On the right, we have a similar plot while looking at the memory usage, which is the amount of memory locked in for a certain amount of time. We see that even though the Xanadu speculative is very expensive in case of memory usage due to a large locking period, Xanadu JIT successfully decreases it to only 2.18x. Thus, Xanadu JIT eliminates CCS without considerable increase in resource requirements. Finally, we look into the case of conditional branches. That is, in cases where the MLP algorithm might fail. We considered Xanadu JIT and Xanadu Speculative's performance against Xanadu Cold for 100 different trees of different configurations and different probability distributions. This scatter plot shown over here shows the performance of Xanadu Cold against these two against Xanadu's speculative and JIT form. We see that on an average, the improvement for Xanadu JIT and speculative is around 29 to 45%, while at the same time, the resource cost is minimal, that is 1% for CPU and 2.7x for memory, while Xanadu is working in JIT mode. That is an overall view of Xanadu, which uses speculative deployment to mitigate cascading cold starts, while at the same time uses just-in-time deployment and a probabilistic model-based most likelihood path to reduce resource requirements. The source code for Xanadu is available on our Git repository. For more details, please look into our paper. Thank you.